All right. Hello, guys. My name is Emma Gilliland, and today I'm going to be talking about entropy and Gibbs. And then my topic was explain how the first, second, and third laws of thermodynamics apply chemical and physical processes. So I think first we should start with, just what is entropy. So entropy is a measure of how spread out, disordered, or dispersed a system is. You should be thinking chaos when you hear entropy. You think like how crazy something is, disordered, chaotic. Like, yeah, that's all that is. And then the more chaotic it is, that means like the more positive that entropy term is going to be. So entropy can be quantitatively defined using S equals K ln W. S is the entropy, K is the Boltzmann constant, which is this right here, and then W is the number of energetically equivalent molecular arrangements. Just for funsies, I also included, how to calculate entropy based off of the volume of a system, which is this equation right here. So there's also standard entropy. So standard entropy is just absolute entropy at 1 atmosphere, and then there's kind of four general rules and guidelines that things need to follow for standard entropy. So the first was that standard entropy of a substance is greater in the gas than the liquid phase, and then the liquid has a greater entropy than the solid phase. So we'll talk about this later when we get into thermodynamics too, so we'll come back to that. For two different monatomic species, the one with the larger molar mass has a greater standard entropy. For two substances in the same phase with similar molar mass, the substance with the more complex structure will have the greater standard entropy. An increase in entropy will be seen in melting, vaporization, or sublimation. An increase in temperature, a reaction that has more gas molecules in the product than the reactant, and then we'll talk about that one later too. So I'm a good, kind of picture learner. I really struggle in chemistry because I need to see something, if that makes sense. So here in these two pictures, we can see, something is, a solid or, low disorder, and then it starts, the entropy is increasing, so it becomes more disordered and then very disordered. So solid, liquid, gas, think ice cube, water, and then vaporization. And then here on the right, this isn't really academic per se, but I just thought, uh, I just thought it was funny. So, what is Gibbs free energy? It's used to predict the spontaneity of a system. It's this equation right here. So G equals H minus Ts. And then for a process at a constant temperature, it is similar. You just kind of add some delta triangles in there. And then for Gibbs free energy, there are kind of three things that you need to remember. So if the G is less than zero, or the delta G, sorry, is less than zero, the reaction is spontaneous in the forward direction and non-spontaneous in the reverse. And then you just flip it around. So delta G is greater than zero, the reaction is non-spontaneous in the forward direction and spontaneous in the reverse. And then we've got lastly, the delta G is equal to zero, then it's none of these. It's in the system is in equilibrium. Just some more fun stuff. So the standard thermodynamic properties table, which we've used that a lot in this class, so I didn't feel like I needed to put it in here, but it has a list of the thermodynamic properties, which can be used, to calculate different values in products and reactants and all of that. Lots of fun stuff that we spent a lot of time doing. And then the delta G of F is specific to being at 1 atmosphere of pressure, pure solid or liquid, or 1 molar concentration in 25 degrees Celsius. So good stuff. Once again, I'm a pictures girl, so more pictures. Also, if you ever want the links to these, let me know, send me an email and I'll send them to you because I know you can't click on them through a screen recording and all that. So yeah, this one was really nice. It's very visually pleasing, which I appreciate. And then you have this one on the right. I don't want to say it dumbed it down a little bit, but definitely did. So I appreciate that because I need that sometimes. especially when I'm learning something new. And then, of course, I had to put in, a little funny one. I would make a free energy joke, but no one would gib it. That's how I feel doing chemistry. So, okay, now we'll talk about, the laws of thermodynamics. So, the first law says that energy uh, can be neither created nor destroyed, but only changed from one form to another. So, some real life examples um, that I think of is the ice cube sitting on the counter and melting because that ice cube is going to absorb heat and then melt into water. Another one is a plant performing photosynthesis by absorbing that sun, and then it will convert that energy into a different type of chemical energy. Also, the process of creating beer, through fermentation. So it's fermenting that yeast, which converts into ethanol and carbon dioxide, and then, of course, uh, boiling water. So, liquid to gas, which we kind of talked about earlier with uh, the enthalpy change or entropy change. Sorry. Second law states that for a process to be spontaneous as written, this must be positive. A system must undergo a decrease in entropy to be spontaneous. So, two things that I thought of for this you have your bicycle. Your bike, it's made out of iron, and you left it outside on accident. Um, and, just your luck, it rained. So, your bike is going to begin to rust a little bit. So, that'll happen because the iron and oxygen are more ordered than the rust. So, gonna go crazy with that one. And then another super sad one, you left your coffee out on the counter to cool down. Maybe you forgot about it. But the heat from that coffee is going to transfer out to its surroundings and lose that heat because it's trying to become more, like the system is trying to become more ordered. Okay, the third law of thermodynamics states that entropy of a perfect crystalline substance is zero at absolute zero. This is where it is believed that molecular motion will stop. So, same thing with the ice cube. I'm sorry, I know it's repetitive. You put the ice cube tray in the freezer, and that temperature is going to lower, and so that entropy is going to get really close or zero, depending on how good your freezer is. Um, and then another interesting thing that I thought of was neon gas, when approaching absolute zero, will almost have no molecular motion. Yeah, something super interesting to think about. Neon gas has some cool properties. So, yeah, that was it. Thank you so much for watching.